All right, so the idea is we're now going to have a bunch of new solving questions that are going to use all of our skills for solving for theta like we've had before, but now different identities might show up. So in other words, we've seen these questions a little bit already because we had questions that had like a sine squared plus cos theta equals 1, and we had to use substitution to change the sine squared to 1 minus cos squared. That was a little taste of this. In all of the ones that we've done so far, we've used the first strategy. Can you write things with only one trig function? So when you had a sine squared and a cos, you changed the sine squared to 1 minus cos squared. Now your equation only had cos theta, and you could factor and solve it. So that is a very important strategy, and we've already done this one. But it's also going to come up that your double angle formulas may appear as well. So then you'll switch out a double angle formula for something so that we only have one function. And the other thing is we want to write things with theta only. So if there is a double angle, we'll want to change it so that we're writing in theta only, not 2 theta. Other strategies that will come out, sometimes you can't change things to only one trig function. Then you might be able to factor out a common factor to solve it. Finally, if you don't know what to do, you can change everything to sine and cos and eliminate fractions, just like we've sort of done a little bit with proving, and then see where things go from there. So we'll do a bunch of examples now that are going to be solved for theta. Here's our first one. Cotangent theta is equal to 2 cos theta. Okay? Key thing here is the word solve. You're not going to draw a line because this is not a proof. It won't even be provable. So in this one, I'm looking at things. I don't have a double angle identity. I don't have any sine squareds or cos squareds. All I have is a cotangent and a cos. So I'm going to use my last strategy, change things to sine and cos, and eliminate any fractions. Well, the only thing I can change is cotangent. That's cos over sine. And that changes things to sine and cos, but it involves a fraction. How do I get rid of a fraction? I'd have to multiply this by sine theta. But if I multiply one side of an equation by sine theta, I'm going to need to multiply the other side of the equation by sine theta. And we get sine theta cos theta is equal to 2 cos theta. Oh, actually, sorry. Right? The reason we did that was so that those signs would cancel out. And we end up with cos theta equals 2 cos theta sine theta. Now, there's 2 ways of approaching this at the next step. It is going to be very tempting, but it will lose you a mark every single time, to divide both sides by cos. Can you see if you divide by cos, you get it to one thing. Only sine will be left. And that's a very tempting thing because that's one of our strategies. Okay? The reason that's going to be bad is I want you to look at that equation and say, if cos is equal to 0, is the left side equal to the right side? Well, if cos is equal to 0, what's my left side equal to? 0. If cos is equal to 0, what's my right side going to be equal to? 0. Are those two equal? 0 equals 0? Yes. If I divide by cos, and one of the solutions is cos is equal to 0, I'm dividing by 0. So generally in a solving question, we don't like to divide unless we really have to. And the thing I want you to do every single time before you divide is check if I move things over to the other side. So I'm going to subtract cos on both sides. Is there a common factor? Yes, I can factor out the cos instead of dividing by cos. And by factoring out the cos, that will allow my solution to have cos equals 0 and still get the other solution where sine of theta is equal to a half. Working with this unit circle, where is cos equal to 0? Pi over 2 and 3 pi over 2. Where is sine equal to a half? Pi over 6 and 5 pi over 6. So if you have a double angle in a solve question, you can either solve it with your identities or with multi-revolution question. And the way to determine which is which, the multi-revolution which we've already done before, that's when the only thing you have in that trig equation, the only trig function you have is the double angle, like this example. So here on the left, cos 2x equals root 3 over 2. See how that just has cos with the double angle, no other cos, no other sine, no other functions. In that case, well, as solving a multi-revolution, the first thing you would do is say, well, if 1x is between 0 and 2 pi, 2x is between 0 and 4 pi. Solving it, I'd have cos 2x equals root 3 over 2. That's on my pi plate. What family is that for cos? Pi over 6. It's going to be quadrant 1 and quadrant 4. That's the first time around. Add 2 pi to these. That's the second time around. Then solving for x, divide them all by 2. And all of your final answers are between 0 and 2 pi. So if the only function you have is a double angle one, then you do not need to use your double angle identity. You can solve it as a multi-revolution question. How do we know we should use the double angle identity? Anytime you have the double angle and another trig function, you will always have to use your double angle identity. So in this question here, solve sine 2x equals sine x. The first thing you're going to have to do is change using your identity. The sine 2x is equal to 2 sine x cos x. Instead of dividing, you're going to move things over, make it equal to 0, and factor and so 0 pi and 2 pi, when is cos equal to a half? Pi over 3 and 5 pi over 3. And we solve it. I'm just going to check our domain to make sure 0 and 2 pi are included, and they are. So we are good for our answer here. And finally, let's turn to example number 4. So it says solve the equation 1/2 sine 2x minus cos squared equals 0 over the domain. So we see the 2x. Is this multi-revolution, or is this one going to be one that we're going to use our identity? We have to use our identity because there is another trig function there. So then our first step is changing the sine 2x to 2 sine x cos x. Multiplying this out, and we've got sine x cos x minus cos squared x equals 0. Now we could change the cos squared to 1 minus sine squared, but in this case it's not going to help us because we have a sine x and a cos x. And there's no way to change a single sine x to cos x or a single cos x to a sine x. It only works with sine squared or cos squared. At this point, can we factor? Is there anything in common? there's a cos. So we can factor that out. That's always going to be helpful. And so by factoring it, we know that cos x equals 0 is a possibility. And here, sin x equals cos x. Cos x equals 0, that's from your pi plate. We know that that happens at pi over 2 and 3 pi over 2. When does sin x equal cos x? You might just be able to tell from your pi plate. Quadrant 1, and what other quadrant are they the same? Quadrant 3. Okay? The other thing people do to figure out a sin x, cos x one, when that's the only things and they're equal to each other, if you divided both sides by cos, then you get tan x equals 1. Oops. And tan x is equal to 1 in quadrant 1 and quadrant 3 because it's positive, and you'd get the same answers that way as well. On the back side of your identities, you know, the one where you had all those proofs, on the back side are a bunch of solving questions. Okay? So on the back side of that, these are the numbers that I would like you to do. It is not the circled ones. These are totally different numbers. And then, so this is off the identities sheet. And then from your textbook, questions 12 to 15.